this computer and run these back. I don't know if anybody actually goes back and watches these or not, but they certainly are available in case anybody decides to do so. So this week we're going to be discussing Chapter 6, and we're going to be talking not only about circular motion, but we're also going to be talking about gravitation as well. So we've kind of gone through a lot of Newton's first through third laws. And since we have done that, what we're looking for is now being able to apply it in certain situations and, maybe give us an idea as to how we can model certain types of reality. And one of those types of reality is going to be circular motion. So the summary here for section 6.1 and 6.2, and we'll get to these here before we look at the other summaries, is that for an object in uniform circular motion, the acceleration vector is directed towards the center of the circle and has a constant magnitude of v squared over r. Period is going to be the time required to make one complete circle. So the magnitude of the acceleration vector can also be written as this, and we'll go through the mechanics of how we get to that. So, provided that an object can be treated as a particle, circular motion is governed by Newton's second law. Because the net force vector points in the same direction as the acceleration vector, an object in uniform circular motion is acted upon by a net force that directs it towards the center of the circle with this magnitude. That probably does not come as much of a surprise. Let's take a look here. All right. So we've got this particle and it's moving around in the circle. Now, in this situation, the magnitude of the velocity is going to be constant. However, the direction of this velocity is going to change. And the way it changes is such that the acceleration of this particle, if you look at the vector notation of it, is going to be such that it's pointing in towards this part of the circle. And if you look at that going all the way around the circle at all different points, what you find is that the acceleration at all of these points end up pointing to a specific center of a circle. So this situation here is going to be considered to be uniform circular motion. So particle moving in a circular path with constant speed. There's no component of acceleration that's parallel to the instantaneous velocity or tangent to the path, otherwise the speed would change. So this is what it ends up being. Now the magnitude of this is going to be constant and is going to be given in terms of speed and the radius of the circle. So when an object moves at a constant speed around a circle, then the magnitude of its acceleration is going to be proportional to the square of its speed and inversely proportional to the radius of the arc. So since it's acceleration, our units are going to be meters per second squared. And this is going to be a reminder that at each point, the direction of the acceleration is radially inward. And the magnitude of this is going to be constant. The vector direction of this is constantly changing, of course, as the object goes around, but it always points towards the center. And this acceleration is sometimes referred to as centripetal acceleration. So we can also take this particular arrangement, that's v squared over r, and we can change it around. We know that the speed at which this object travels is going to be some rate. It's going to be some length of measurement divided by time. We know that it goes around the entire circle of radius r. We know that's the velocity. And we also know that the amount of time that it takes is going to be the measured period. We can get a measurement of that. So when we put this in for what we see over here, then we find out that the radial acceleration is going to be 4 pi r divided by the period squared. So we've often used T to denote the tension in a rope or string, but here we're going to have it represent time. It's going to be a period of or a certain length of periodic in which periodic motion occurs. So force as defined by tension is going to be represented with this nomenclature going forward. So the device that you see here is going to be something called a centrifuge. It is used in labs to purify and analyze biological specimens, particularly those in a liquid that contain suspensions. If a precisely balanced rotor contains the specimens, and it can be spun faster than 10,000 revolutions per minute with centripetal accelerations of up to 10,000 grams. Different components of the specimen have different densities and tend to separate, with the denser components migrating to the radii that have the longer paths, the outer part, so that you can get at the different components there, which is kind of neat. So it's an actual application here of what we're studying. So if we're going to define force as mass times the acceleration, and now we know what the acceleration is in this case, then the centripetal force is going to be equal to mv squared over r. So the quantity here is not a force in the sense that it's actually real. It's actually used to model what's going on. It's a great model, but we don't actually have centripetal force. There's nothing specific that's causing this object to go in. There's no specific force there. That's just how we're using to model it. So let's see here. So here's an example of how the equation is going to apply to circular motion. So we've got a ball that whirls on a string attached to a rotating peg in the center of a frictionless table. So, and then suddenly when the string breaks, it releases the radial force on the ball. So no net force now acts on the ball, so it'll obey Newton's first law. It moves in a straight line with constant velocity. So why did that time out? Let's try refreshing here, see if that'll help. Well, that's not exactly what I was looking for. There we go. Huh. Well, that's too bad. Maybe that'll come up if you go back and look at it a little bit later. All right, so we got some exercises here. We can look at one or two of these before we go further. right, so we've got a small car with mass m and a large car with mass 2m that drive around a highway curve of radius r at the same speed. As they travel around the curve, the accelerations are they equal? Are they along the direction of motion in the ratio of 2 to 1, or are they 0? Well, they all travel at the same speed v. And that's what it's talking about here. The acceleration depends only on the speed and the radius. So they're both driving in the same radius. So both cars have the same speed and radius, so it must have the same acceleration. So in this particular case, the mass doesn't make much difference when we're talking about the accelerations. So now let's take a look at this figure. This figure 6.3 shows a skateboarder moving along in one direction, one straight and two track curves like this. In which picture is the magnitude of the normal force exerted on the skateboarder by the track smaller than his weight? In all three cases, the weight of the skateboarder is directed downward and the normal force on the track points upward. If the normal force has a smaller magnitude than the weight, the free body diagram must look like this. And as we can see from the free body diagram, when we add both forces together, the net force must point downward. Therefore, the acceleration must also point downward in the same picture. So in A, there is no vertical component of acceleration. In other words, he's traveling at a velocity here. There's no up or down acceleration. So this choice cannot be correct. It cannot be such that in that picture is the magnitude of the normal force exerted on the skateboarder by the track smaller than his weight. So in B, where the skateboarder is at the bottommost part or point on the track, then the acceleration is upward because eventually he's going to work his way out of it towards the center of the circular path. In C, when the skateboarder is at the topmost point of the track, the center of the circular path is downward from the skateboarder's position, so the acceleration in this case is downward. So correct choice here regarding the picture in which the magnitude of the normal force exerted on the skateboarder is smaller than his weight. It ends up being this one. So several other examples here to kind of work through and see what's going on. So hopefully you won't have that game, that timing out error. I'm not quite sure why that's popping up. So now let's go to section 6.2. Eventually. There we go. Motion in a vertical circle is no different in principle, but the weight of the object has to be included because it may play a role in producing the necessary centripetal acceleration. So, on a Ferris wheel, at certain parts of the motion, gravity plays a role in providing the necessary radial acceleration. Specifically, at the top of the circle, gravity is pulling towards the center of motion. A passenger moves in a vertical circle of radius r with constant speed v. So assuming that the seat remains upright during the motion, derive expressions for the magnitude of the upward force the seat exerts on the passenger at the top and the bottom of the of the circle if the passenger's mass is m. So what are the forces if the passenger's mass is 60 kilograms and the radius of the circle is this, and the wheel makes 1 revolution every 10 seconds? So we're going to set this up, and this shows our sketch of the Ferris wheel with free body diagrams for the passenger at the top. So this is a little stick dude, and we're looking at radial acceleration this way, and we're looking at the velocity going that way. And then down here, when it comes back down, then the velocity is that way, and the mass is, well, whatever the mass is. And then the radial acceleration is pointed this way. So at these points, the forces and accelerations have only vertical components. We're going to take the positive y direction as upward in both cases. We're going to use n sub t and n sub b to denote the magnitude of the force the seat applies to the passenger at the top and the bottom of the wheel. So we've got sketches for the two positions. We've got our sketches for this particular problem. We know that the radial acceleration is pointed down this way. We know the weight's pointed down this way, and we know the normal force is pointing up this direction. So if we look at a free body diagram, we look at the bottom, and then we know the weight is still pulling down. We know the radial acceleration is up, and we know that we have the normal force here acting again on the passenger. So we're going to derive expressions for the magnitudes of n sub t and n sub b. We're going to use Newton's second law for the y component. So notice that this sign is negative at the top of the wheel, but at the bottom, it's going to turn positive. The y component of weight is negative, but the y component of these two is going to be positive. So for the top of the Ferris wheel, we know that this is the acceleration. We know we have the normal force here, and then we subtract out gravity. Rewriting this, this is what we come up with. So the top of the Ferris wheel, the upward force the seat applies to the passenger is going to be smaller in magnitude than the passenger's weight. The bottom of the circle, the acceleration is going to be upwards. So we're going to change that to positive. Now the orientations of those are still going to be the same. This is what it ends up being. So at this point, the upward force provided by the seat is always greater than the passenger's weight. And in other words, you can feel the seat pushing up on you more firmly than when you are at rest. So if we want to calculate these normal forces for a 60 kilogram passenger with this radius and this period, we know how the velocity is computed, which is to say 2 pi r divided by t. Run through all of that, we get that. Magnitude of the radial acceleration we know is going to be v squared over r. And so this is what it ends up being. So the two forces at the top and the bottom are going to be your mass in each case, which isn't changing. And then we need to find the acceleration. Now, we know what the gravitational acceleration is. We now know what the radial acceleration is. On the top, we know to subtract it because it's not working in the same direction as gravity. At the bottom, we have the same value here, but we're going to add this because it's pointing up, pointing in the same direction. So passenger's weight is 588 newtons, and these are respectively about 30% less than or greater than the weight. Anyway, that's one set of problems that you can work through. You'll be able to get a better idea here of motion in a unit circle. Okay. So we've got Newton's laws of gravitation. That's the next section, section 6.3. So if you've got two particles with mass m that are a certain distance r apart, they are going to attract each other gravitationally with these forces of motion being described here. These forces form an action-reaction pair in accordance with Newton's third law. If the objects cannot be treated as particles but are spherically symmetric, this law still holds. R is just going to be the distance between the centers. Gravitational interaction of a spherically symmetrical object from any point outside the object is just the same as though all of its mass were concentrated at the object's center. Okay. So, Newton discovered the laws of gravitation about 300 years ago. Gravitational force being categorized as the weight of an object, the force that attracts it towards the Earth. Newton discovered the laws of gravitation during his study of the motion of planets around the sun and published it in 1686. So that's a while back. So every particle of matter in the universe attracts every other particle with a force that's directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. So we got two particles, they have two different masses, they're separated by a distance r. Newton's law of gravitation ends up being this. We also know that the force of gravity of 2 on 1 or 1 on 2 can be written as this. Forces of the gravity have the same magnitude. You also have G. This is going to be a universal constant that we have to deal with when it comes to gravitation. So the gravitational attraction between two particles is going to obey Newton's third law. The force always acts along the line, joining the two particles, and it forms an action-reaction pair. Even when the masses of the particles are different, the magnitude of the gravitational force on each particle is going to be the same, but respective forces pull in opposite directions. So for an instance, when a ball is thrown up in the air, the force the Earth applies to the ball, which is going to be the ball's weight, has the exact same magnitude as the force the ball exerts on the Earth. So we've stated here that the laws of gravitation in terms of the interaction between two particles. The interaction between any two objects that have spherical symmetric mass distributions, such as a solid sphere or spherical shells, is going to be the same as though all the mass were concentrated at its center. So in other words, if we take these objects and we condense them down to a center, we can still model the gravitational force on each object. So at points inside the Earth, the situation is going to be a little different. If we drill a hole through the center of the Earth and we measure the gravitational force on a particle at various depths, we would find that the force decreases as we approach the center. In other words, rather than increasing at this particular rate. As you enter the interior of the Earth, some of the Earth's mass would be on the side of the object opposite from the center when pulled in the opposite direction. And exactly at the center, the gravitational force on the object would be 0. So Determining the value of the gravitational constant means that you have to measure the gravitational force between two objects with known masses. And for bodies of reasonable size, the force is extremely small, but it could still be measured with an instrument called a torsion balance. You may have heard of that. And the Cavendish balance consists of a light, rigid rod shaped like an inverted T, which is what all of this is going to describe, supported by a very thin vertical quartz fiber. So you've got a quartz fiber here. Two small spheres, each of mass M1, are mounted at the ends of the horizontal arms, and when we bring two small spheres, each of mass 2, to the position shown, the attractive gravitational force twists the T through a small angle. We measure the angle by shining a beam of light on a mirror fastened to that T, and the reflected beam strikes a scale, and as the T twists, the beam moves along the scale. So you've got gravitation that pulls the small masses towards the large, causing the vertical quartz fiber to twist. The small balls reach a new equilibrium position with the elastic force exerted by the twisted quartz fiber, and that balances the gravitational force between the masses. And the deflection of the laser beam indicates how far the fiber is twisted, and once the instrument is calibrated, this result will give you a value for G. For most of our purposes here, we're just going to use the value of G. We're not going to worry about trying to compute it. All right. So if we have our Cavendish balance, so let's take a mass M1 of one of the small spheres, and then the mass 2 of one of the larger spheres, and then the center-to-center distance between each sphere and the nearest small one is going to be this. So find the magnitude of the gravitational force. Well, we know what the gravitational constant is. We know what each one of these weigh. We know what the distance is between the center to center. We go through and compute the actual gravitational force. So there'll be a few problems like this to go through here on the homework. Now the weight. The weight of a body is the total gravitational force exerted on it by all other bodies in the universe. And near the surface of the Earth, the object's weight is very nearly equal to the gravitational force exerted by the Earth alone. In other words, that's going to be your dominating contribution to the force. If the Earth's magnitude is m sub g, the weight of an object of mass m is going to be given by this. Acceleration due to gravity is going to be given by this. Okay. I bet you've never heard of something called a gravity map of the Earth. So protrusions represent areas of stronger gravity because of non-uniform mass distribution, and dips show areas of weaker gravity. So if you look at the weight of an object near the surface of the Earth, if we model the Earth as a spherically symmetric object, which physicists are known to do, with a radius r sub e and mass m sub e, and the weight of a small object of mass m at the Earth's surface is going to be given by this particular formula. And that's an extension of what we've just seen. This can also be used to calculate the weight on other planets or moons. And it also works for objects that are at a height 8, a bunch that are above the Earth's surface. so long as you're not that much further, or as long as this is much, much smaller than the radius of the Earth. So we know from section 4.4 that the weight of an object in its mass times acceleration of free fall of the location of the object, weight is equal to mass times gravity. So if you take this right here, you know the mass times gravity is going to be equal to this. Acceleration due to gravity near the Earth's surface. So you've got gravity near the Earth's surface, you got the units. You can obtain the acceleration of gravity near the surface of another planet by replacing the mass and radius of the Earth with corresponding values. So, because 6.7 because this does not contain m, the acceleration due to gravity is independent of the mass of the object. So we already know that, but we want to see how that follows from laws of gravitation. So we can measure all of the quantities in 6.7 except for this, because you can't really put the Earth on a scale. So this relationship is going to allow us to compute the mass of the Earth. So if we solve this for m sub e, we come up with this. If we know what the radius of the Earth is, we know what the gravitational acceleration is, we find out that this is the mass of the Earth. In other words, we took nothing more than what we use to analyze certain problems with and just certain deductions, and we've measured an object that you could never put on a scale. And that's pretty fascinating. So the gravitational force is going to be proportional to 1 over r squared, and the weight of an object decreases inversely with the square of its distance from the center. So if you follow this particular chart here, you've got the Earth represented here. You have a certain radius of the Earth that's out here, and this is a certain distance above the Earth's surface. As you continue to rise above the Earth's surface, you'll notice that the mass continues to just kind of drop off. Because you got the weight, or your weight up here, you've got the astronaut up here, you can kind of move him here and there if you want to. His weight begins to decrease the further out that you go. So, using these values, we're going to determine the average density of the Earth. We know that 4/3 pi r cubed is going to be the volume of a sphere. So if we know the radius of the Earth, we can go ahead and put that in. So this is how much volume is going to be there. Take the mass divided by the volume, that gives us the average density. You go through and you look exactly at what the Earth consists of. You've got solid mantle here, you've got a molten outer core, you've got a soft inner core, and then got everything lying on top. Okay, so you got a few more problems there to work through. And then finally, we're going to look at satellite motion. So when a satellite moves in a circular orbit, the centripetal acceleration is provided by the gravitational attraction of the astronomical body that it orbits. So if a satellite orbits the Earth in an orbit of radius r, the speed and the period are going to be represented with this. Now, you may have heard of something called a black hole. A black hole is going to be an aggregation of matter that's so dense that nothing can escape its gravitational acceleration, not even light. So a non-rotating spherical distribution of mass is a black hole if its total mass is contained within the radius of less than this. It's called the Schwarzschild radius, where c is the speed of light. That's not something that most of us will have to worry about. There we go. Well, kind of. Oh, for Pete's sake. All right, there we go. Satellites orbiting the Earth differ only in scale, not in principle, from the motion of our moon around the Earth or the motion of the planets. So we're going to assume that the satellite moves in a perfectly circular orbit. By combining what we already know about the dynamics with Newton's general theory of gravity, we should be able to develop a mathematical description of the motion. So, what do we need to know about projectile motion? So when you fire a paintball from some distance above the ground, it follows a parabolic path until it strikes the ground. Or a motorcycle rider rides horizontally off the edge of a cliff, landing him in a parabolic path that ends on the flat ground at the base of the cliff. Well, at least I hope it's that. I mean, it's not really drawn in there, is it? So could end up on a bunch of alligators there. That would be bad. But if he's driving at a speed here, you will see that this is going to be his trajectory. If the biker survives and repeats the experiment with an increased launch speed, he's going to land further away from the starting point. That makes sense. So if he does it again and again and again, and each time increasing the speed, if he does it with a great enough speed that the Earth's curvature becomes significant, and as he falls, the Earth curves away beneath him. If he goes fast enough, and if his launch point is high enough that he clears the mountaintops, he might actually be able to go right on around the Earth without ever landing, which is kind of neat. So let's take a look at this figure. We're going to launch a projectile, A, in the direction tangent to the Earth's surface. So we're going to launch it horizontally. Trajectories 1 and 7 are going to show the effect of increasing the initial speed. Trajectory 3 just misses the Earth. Just misses. And the projectile has become an Earth satellite. If there is no retarding force, such as air resistance, the projectile speed when it returns to point A is going to be the same as its initial speed, and it repeats the motion indefinitely. So got 6 and 7 here. You've got the projectile launched tangent to the Earth's surface at successively higher speeds. So you started out at 1 here and didn't go very far. And then you started at 3. That's when you start to hit an elliptical orbit. Let's see the ellipse around right here. At 4, you start to see a circular orbit. 5, again, you go back to an elliptical orbit. And then eventually, if you get to 6 and 7, then the projectile is launched at such high speeds that it's going to escape from the Earth. So, Circular orbit is going to be the simplest case and is the only one we're going to look at. Artificial satellites often have very near circular orbits, and the orbits of most planets around the sun are almost nearly circular. We know the speed or the acceleration of the radial acceleration in uniform circular motion. And we know that's always directed towards the center of the circle. So for a satellite of mass m, the force that provides this acceleration is the gravitational acceleration of the Earth. So if the radius of the circular orbit measured from the center of the Earth is r, and then the gravitational force is going to be considered to be this. So principles governing the law of governing the motion of the satellite is Newton's second law, F is equal to ma. So the gravitational force and the acceleration are going to be equal to one another. If you go through and if you solve for v, this is what you come up with. So to find the speed of a satellite around a planet other than Earth, we simply replace this with the mass of that planet. So the period of the moon's orbit about the Earth is about 4 weeks. If the mass of the moon were suddenly reduced by a factor of 2, how long would the period of the moon be? So let's see here. Get this opened up. Guess not. But if you look at this particular equation, you can see that the orbital period of a satellite is independent of the mass of the satellite. And the period does depend on the mass around which it's orbiting. The correct answer here is A. All right. Equation 6.8, this guy right here, shows that we can't choose the radius r of the orbit and the speed of the satellite independently. If we choose a value of r, then v becomes determined. It also shows that the satellite's motion does not depend on its mass because it doesn't appear anywhere in the equation. So we could cut it in half without changing the speed, and each half would continue on with the original motion. So again, if we know the speed, which is 2 pi r divided by the period for one revolution, we substitute that information into here, crank through, we find out that this is going to be the period of the satellite. So up to this point, we've talked about artificial Earth satellites, but we can also claim the same analysis to the circular motion of any object. This includes planets. Observations of satellite motions can be used to determine the masses of the planets in our solar system and of many other astronomical objects. So, for example, Jupiter has more than 30 moons. The orbital radii and period of many of those have been measured by astronomical observations. So the appropriate relationship is going to be 6.10, where we go through and we replace ME with M of Jupiter and then solve for the mass of Jupiter. So we take all this information, put it in, and solve for the mass of Jupiter. If the orbit radius r and period t of a satellite of Jupiter can be measured, then we can calculate its mass. So a more dramatic example of this type of analysis is through the discovery of black holes. Not sure if you're familiar with what a black hole is, but it's basically a lot of matter that is so massive and dense that nothing can escape from the gravitational field. So in 1916, Charles Schwarzschild, there we go, Carl Schwarzschild, there we go, predicted on Einstein's general theory of relativity that if an aggregation of matter with total mass m had a radius less than some particular value, called the Schwarzschild radius, then nothing can escape from its gravitational field. And this is a calculation of the Schwarzschild radius. So, the surface of a sphere with radius r sub s surrounded by a black hole is going to be called an event horizon because light can't escape from that sphere. All we know about a black hole is going to be its mass, its charge, and its rotational characteristics. And this is what one of these look like. A lot of times you're going to find these things fairly close to like a binary star. Or this used to be a binary system, but one of these stars collapsed. When it collapsed, you can see a bunch of radiation being emanated from the top and the bottom, and then you've got the characteristic look, and then it is draining the gas off of its companion. So, what does it mean to say that an astronaut orbiting the Earth in a spacecraft is weightless? The Earth's gravitation is still acting on the craft and its occupants, as it must to provide the centripetal acceleration that keeps the craft in orbit. Yet the environment seems to have no gravity. So, a companion or an allegory to this is going to be a person standing in an accelerating elevator. Let's see. Just load up. So something like this. If the person stands on a spring scale, the scale doesn't read the true rate of the person during the acceleration. Now, suppose the elevator cables have all broken and all the safety brakes have failed. So the elevator and its contents are in free fall, downward acceleration of magnitude of gravity. What does the spring scale read now? The scale can't exert any upward force on the person, otherwise her acceleration would be less than g. So the scale has to read 0, and the passenger seems to be weightless, even though the Earth's gravitation still acts on her, and her actual weight hasn't changed. If, in the excitement of the moment, she lets go of her purse, it won't fall to the floor because it's already accelerating downward with the same acceleration as the elevator. So, that's part of how gravity works. Our bodies can't directly sense the force of gravity, but we can sense the forces of conduct that are induced by the gravitational tug of the Earth. So, for example, include the force the floor applies against our feet, and the force the suitcase applies in our hand as we carry it. We're able to directly feel gravity, and being able to do that does not offer any clear-cut advantage. So, and then you've got some historical footnotes there. So that's the basics here of chapter 6. Just basically, it's an application of Newton's laws in the form of gravitation, and then also discussing uniform circular motion, which actually is going to come in handy a little bit later on. Do you guys have any questions? I know I was blathering on there a little bit, but that is the general summary of the chapter. One thing I will mention here is that on lab number 2, I had to go back and restructure it such that in the flash player was no longer needed to complete that lab. they don't make Flash Player anymore, and the previous lab had that in it, so I went ahead and re-recorded and re-uploaded the adjustments. So hopefully that won't slow you down. So, okay, if you guys don't have anything or don't have any questions, that will be it for this week. And next week we'll go over chapter 7. Does that sound okay?
Yep. Thank you.
Mm-hmm.
Yep, sounds good. Thank you.
Okay. All right. Y'all have a good evening. Okay.
You too. Bye.
You too. Bye.
Bye.